So this is the 26th lecture, and in the last lecture I discussed the energy band diagram with you, that if it is an isolated atom, in an isolated atom you have energy levels, and when it is a crystal, in case of a crystal, in the outermost shell, I took an example of a silicon. You have an empty conduction band, then a filled valence band, and in between you have a forbidden band. Now based on this forbidden band, the solids are divided into conductors, semiconductors and insulators. So let me redraw this figure once again, that if this is the energy, suppose I say that here you have the energy, and if this is the valence band, this band I am representing this by this particular band as by a valence band. I represent this by VB. This VB stands for valence band. When I say VB, this VB means valence band, and when I write CB, that CB means conduction band. Conduction band here. Now if there is, almost theoretically there is no gap between this valence band and conduction band, if it is here only, that is they almost overlap. This is your conduction band. So the solids which come under this category, they are known as conductors. These are known as conductors. That is, this energy gap, if I say that this energy gap or this forbidden band which is represented by Eg, this Eg is approximately equal to 0 in this case. On the other hand, in case of semiconductor, when I take the case of semiconductor, say this is energy on this side, this is a valence band here, this is valence band, and this is conduction band, for example. This is your conduction band. Now if this energy gap, this is Eg, I represent this by Eg, this energy gap, in this case if it is less than approximately 2 electron volt or 3 electron volt, this energy gap, this is your again valence band and this is the conduction band, such metals, I can say it comes under, or such elements come under the category of semiconductor. We call them as semiconductor. And this energy gap in general, normally we use as semiconductor as germanium and silicon. This, of course, gallium arsenide is also there, but we'll consider germanium and silicon. For this, for germanium, this energy gap Eg, when I say this Eg for germanium, this is equal to approximately 0.69 or 0.7 electron volt. And for silicon, this Eg or energy band gap or this forbidden band is equal to 1.1 electron volt approximately. So these comes under the category of semiconductor. On the other hand, if I talk about the insulators, they have a large forbidden band. A large forbidden band is here. This is again, this is a valence band VB, and I show that this is your conduction band. This gap is as high as, I can say that this Eg is, I can say it is greater than or equal to 5 electron volt. Such large energy band gap is there. Of course, this conduction band. Then these comes under the category of or these are called insulator. So the energy band gap is, or I say the forbidden band gap is minimum in case of conductors, then moderate in case of semiconductor, and very large in case, this is energy, very large in case of your insulators. It means if I have to push an electron from valence band to conduction band, here I require a large amount of energy is required in order to push an electron from valence band to conduction band. Now as far as the conductivity is concerned, I can say that the conductivity of this, suppose I say this conductivity, I represent this by sigma. Conductivity of conductor is maximum. Conductivity of conductor is greater than the conductivity of semiconductor and this will have, insulator will have 0 or I can say minimum conductivity of insulator, where the sigma represent the conductivity insulator. On the other hand, if I talk about the resistivity rho, this rho is maximum in case of insulator. I am representing this by I means for insulator. Then this is for SC means for semiconductor, and then I'll say resistivity is minimum for a conductor. This is conductor. Let me recall what do you mean by this conductivity and resistivity. It says that suppose this is a material of length L. This is a material of a conductor, or it can be a semiconductor of length L, and suppose I say that the cross-sectional area of this is A. Then we know that the resistance of this material is directly proportional to the length and inversely proportional to the cross-sectional area, or I can say that this R is equal to rho L upon A, and this rho which is equal to RA upon L. This is called, this term is called the resistivity. We call this as, let me name this rho is known as resistivity. On the other hand, the reciprocal of this rho, or I can say this 1 upon rho, I continue from here. After this I am writing here. The reciprocal of this rho, that is 1 upon rho. 1 upon rho means it is represented by sigma, and if I reciprocal of this will be L upon RA. This L upon RA, reciprocal of this rho, this is known as, this term is known as the conductivity. You have done all these things in your junior classes, so I am not going into detail of this. So this is called the conductivity. So the conductivity of conductor is highest, then moderate in case of semiconductor, and then insulator. But why still we go for semiconductor? I'll come to that part. This conductivity of semiconductor is controllable. The point is that. Otherwise we would have used conductor only. So this is about the differentiation between this conductor, semiconductor and insulator on the basis of energy diagram, or somewhat between on the basis of this energy band gap, or on the basis of this conductivity and resistivity. So let's move to some few more definitions of this. In case of conductors, semiconductors and insulators. Another definition that I will discuss today is mobility altogether. Next topic is mobility and drift velocity. What do you mean by these terms? Then I'll move to semiconductors straight away. Mobility and drift velocity. What do you mean by this mobility and drift velocity? Now just try to understand this, that suppose I said that this is a conductor here. Suppose I say that this is a conductor here. Now this conductor has some electrons, of course, either in valence band or conduction, in valence band suppose. Now these electrons are in random motion in any direction, in a zigzag direction. And these electrons, of course these are electrons. These electrons does not contribute anything in the conduction of the current. But suppose the same conductor I take and I apply an electric field here. If I say that the length of this is L, and if I apply an electric field, that is I apply a battery here which is acting as an external energy source, I apply, and of course when I apply a voltage V here, an electric field will be developed which will be equal to V by L. Electric field is the potential gradient, or I can say the voltage per unit length. This is called the electric field. So electric field will be developed here. So what will happen, that these electrons, I am showing now this by E, negative charge electrons. These electrons which were moving in any random direction, now they move according to this electric field, and of course they'll move in this direction from negative to positive. So they'll be, and the movement will be aligned in this direction. You'll have the movement of these electrons from negative to positive in this direction, according to direction of this electric field. I hope that this point is clear to you. Now what happens, that on the application of this electric field, you have a large number of electrons here. So they have certain velocity, they are moving with certain velocity, and since there is a large number of electrons, we say that they don't simply move, but they drift, because the number of electrons is very large. So they drift with certain velocity. On the application of this electric field, that velocity is known as drift velocity. So drift velocity is nothing, the velocity with which these electrons in a conductor or in a semiconductor, they drift on the application of an electric field, is called the drift velocity. And this drift velocity is represented by V with a suffix d. This V represents the velocity, small v, and this d, of course capital V I use as a voltage, so I am using this as a small v. So small v for velocity, and d as a drift velocity. So it is very clear that this drift velocity Vd, this drift velocity Vd is directly proportional to applied electric field. This Vd is directly proportional to the applied electric field. Larger is the applied electric field, naturally drift velocity will be more. And in order to remove the sign of proportionality, we say that this Vd is equal to mu into E. And this mu is called, this mu which is equal to Vd by E, this mu is called the mobility. Mobility of this particle, either electron or hole, is called the mobility. This is called mobility. So this mu is equal to Vd upon E. You can derive the unit of this also. If I say what is the unit of this, the unit of this, you know that Vd, velocity, is meter per second. Meter per second, the unit of this mu. Vd, velocity, distance upon time, your displacement upon time, and this is E, is V by L. So V is, it is V by L. So this is, if you see that this V is volts, it is volts, and length is in meter. So meter square per volt second. If I say what is the unit of this, it will be meter square per volt second. This is a unit of this mobility. So I hope that this drift velocity and mobility is clear to you. Drift velocity is nothing, it is the velocity with which these electrons or these charged particles, they drift on the application of an electric field. So I hope that this is clear to you. One more concept that I will discuss before coming to semiconductor, that is called hole. Let me use some other. I'll use hole concept. What do you mean by hole? Hole, or what is a hole concept actually? H-O-L-E, hole. This concept is used only in semiconductors. Now just try to understand this. What do you mean by this hole? What happens that when I apply some energy to this, some external energy is applied to this particular electron which is in the valence band here, which is in the valence band, as I told you in the last lecture, that this is a field. Initially it is filled with the electrons. Now when I supply some energy to this, electrons in this, they'll cross this forbidden band and shift to the conduction band, where they are ready for conduction. For conduction, these electrons must have sufficient energy in order to constitute some current. So when I apply some energy here, what will happen, that these electrons, they move in this direction. They move from valence band to conduction band, and this electron is here. Say this electron here. This electron has moved from this place to this place. Now what happens when a negative charge, this electron has a negative charge, there will be a vacancy of a negative charge here. So whenever an electron is released from here, comparatively a positive charge is left behind, and this positive charge which is left behind after the release of an electron is called a hole. So this is called a hole only. That is, whenever you have an electron here, suppose I say that this is an electron here, this electron moves in sorry, it moves from this position to this position. Okay, let's take it vertically only. For example, it is moving from here to here after the application of some electric field or some external energy. What will happen that when an electron is released, because of the release of an electron, a positive charge is left behind, which is called a hole. This is a hole. Similarly, when this electron, it will move from this side to this side. This electron is here. So, and further, this electron moves here. What will happen when this electron moves here from this point to this point? You will have a hole here. A hole is created here. A hole is created here. So hole is nothing but it is the positive charge left behind after the removal of a hole, that of an electron, that is called a hole. Now as far as the direction of hole is concerned, the movement of direction of hole is concerned, if the electrons are moving in this direction, so apparently the holes are moving in this direction. So the direction of the flow of holes is always opposite to the direction of flow of electrons. One more thing, if you know about the current, see this conventional current, we say that if this electrons are flowing, let's take another, I'll take another figure. If I say that there's a conductor here, or it can be a semiconductor. Initially I'll deal with conductor only. Suppose there's a conductor here and I apply an electric field here. Electric field means it can be developed with the help of a battery here, if the length of this is L. Suppose I say that these are the electrons. These are electrons. The electrons are moving in this direction. Remember that. These electrons, they are moving from, they will be attracted towards the positive terminal of the battery. It will supply some electrons here. So electrons are moving in this direction. And remember that the conventional current I is always taken opposite to the direction of flow of electrons. This is the conventional current. This is the conventional current if the electrons are flowing in this direction. Now one more thing, if the electrons are flowing in this direction, it is very clear that the holes will flow in the opposite direction. It is very clear that the holes, let me show with a different color here, I'll use black one. So if electrons are flowing in this direction, it is very clear that the holes are flowing in this direction. I have written this holes, H-O-L-E-S, please. If it is not clear, let me write it again. It is holes. So if the electrons are flowing in this direction, it is very clear that the holes are flowing in this direction, or I can say that the conventional current, the sign convention of the current, is either opposite to the direction of flow of electrons, or I can say it is in the direction of flow of holes. So remember that very first thing is that moment of electrons is in this direction, then the moment of holes is opposite to the direction of flow of electrons. So I hope that this whole concept is clear. Hole is a concept. Remember that hole is not a particle. Proton is a particle. Hole is a positive charge left behind after the release of an electron. So, and now I'll come to the classification of semiconductors. Let's come to the, now I move to semiconductors and classification of semiconductors. We have discussed that having energy band gap between 0.7 to 1.1 electron volt or 2 electron volt, they comes under the category of semiconductor. Now these semiconductors are classified into two categories. One is called the intrinsic semiconductor. First is called the intrinsic semiconductor. intrinsic semiconductor. They are divided into two categories, and the other is called the extrinsic semiconductor. Now, these intrinsic semiconductor are also known as, they are the pure semiconductor. That is the semiconductor which are in the purest form. These are pure semiconductor, and these are the impure semiconductor, and our focus is mainly on this extrinsic semiconductor only. These are called impure semiconductor. Now, impure means it is a semiconductor only. A pure conductor is made impure by adding some impurity in this. So it is very clear that if you have an intrinsic semiconductor, you have an intrinsic semiconductor, and if I add some impurity, if some impurity is added to this pure semiconductor or intrinsic semiconductor, the resulting semiconductor is an impure semiconductor, or it is an extrinsic semiconductor. The resulting semiconductor is a extrinsic semiconductor, and this process of adding the impurity to a pure semiconductor, I am adding some impurity to this pure semiconductor. This process of adding an impurity to the pure semiconductor in order to make it an extrinsic semiconductor is known as doping. That is, when a pure semiconductor is doped with some impurity, the resulting semiconductor is an extrinsic semiconductor or an impure semiconductor. So this is one more definition which is many times asked in the examination, that what do you mean by doping. So I hope that today these concepts are clear to you, that how this is classified on the these metals are classified into conductor, semiconductor and insulator on the basis of energy band diagram. What do you mean by conductivity, resistivity, what do you mean by mobility, drift velocity, what is whole concept, and classification, what do you mean by doping. So I'll stop it here. In the next lecture I'll deal with these intrinsic and extrinsic semiconductor. Further, before I wind up for today, these extrinsic semiconductor are further subdivided into N-type semiconductor and P-type semiconductor. So in the next lecture I'll deal with this N-type and P-type semiconductor. So I'll stop for the time being. Thanks.